In the last video, we have discussed about motion of a body on a circular track or a circular path. Now we are going to discuss some examples and then we will see how we can use those concepts here to solve the problems. Here we have example 4.10. A cyclist speeding at 18 km per hour on a level road takes a sharp circular turn of radius 3 meter without reducing the speed. Okay, here the speed of the cyclist is given and the turning radius is given and the coefficient of static friction between the tires and the road is also given. Now we have to find out whether this cyclist is going to slip or whether he is going to make the turn successfully. So let's check what is going to happen here. So on the flat road or a flat circular track, the maximum permissible speed, we already discussed about it. It should be, this is maximum speed. This should be mu s, that is coefficient of static friction, and then radius of the track, and then acceleration due to gravity. So we have discussed this thing in our previous video. So we can check here. Mu s is nothing but 0.1 into r, that is 3 meter, and g, for simplicity, we can take 10. Then we will have under 3, and all these things are in SI system. So this will be meter per second. Okay. Now, the cyclist is taking this turn at a speed of 18 kilometer per hour. So speed of the cyclist is 18 kilometer per hour, or we can convert this kilometer per hour into meter per second so that we can make this comparison easy. So 18 into kilometers, we can convert 1000 meter, and hour we can convert into second, which will be 3600 second. So this will be 5 by 18, and then ultimately it will be 5 meter per second. So here we can see that maximum permissible speed without slipping is nearly 1.7 meter per second, but cyclist is taking turn at a greater speed compared to that. So here this cyclist is going to skid on the track. Okay, moving to the next problem. We have the question. A circular racetrack of radius 300 meter is banked at an angle of 15 degree. If the coefficient of friction between the wheels of a race car and the road is 0.2, then we have to find optimum speed of the race car to avoid wear and tear on its tire and maximum permissible speed to avoid slipping. Okay, we will start with this problem, a second one. What is the maximum permissible speed? So we have discussed in our previous videos that the maximum permissible speed in this case is Vmax is Rg, and this expression actually. So this is Vmax equals to Rg, and then we have mu s plus tan theta divided by 1 minus mu s tan theta, and square root of this entire expression. Okay, so here we have R 300 meter, G we can take if nothing is mentioned. Okay, for simplicity we can take 10 meter per square second, or we can take 9.8 meter per square second, and then theta here is 15 degree, and mu s is also given, that is 0.2. So we can calculate this thing, and after calculating this thing, we are going to get Vmax equals to, we need to just put these values in the expression and we need to calculate this Vmax, and it will be 38.1 meter per second nearly. Now moving to the part A of this problem. What is here? Okay, we have to determine optimum speed of the race car to avoid wear and tear on its tires. So what do we need to do here? We have to find the optimum speed at which the car can take the turn without help of static friction there, because the friction is there which is responsible for wear and tear of the tires. So if the car is taking turn without help of this static friction, with the help of only horizontal component of the normal acting on the car, let's refer to our diagram while we were using while discussing about these things, then it will be more clear. Okay, referring to this diagram, we can say, look what is happening here. For centripetal force here, we can see one component from this static friction is contributing, and of course horizontal component of this normal reaction is also contributing to the centripetal force. So what we need to do here, we have to consider the velocity with which this car can make the turn with the help of the normal, with the help of the horizontal component of this normal force only, without taking help of this component of this static friction. So we have the expression for that. Okay, here we can eliminate these terms, and then we can get the desired equation to find out the optimum speed. So in that case, if this term is 0 and this term is 0, so here it will be tan theta only. So we optimum in this case will be rg tan theta and whole thing under square root. So we can write under root rg tan theta, and we can calculate this thing. We have r given here 300 meter. G we can take 10 meter per square second for simplicity, or we can take 9.8 meter per square second. And then we have theta, which is 15 degrees. So we can take tan 15 here. And we can calculate the things given here. And then we will have the final velocity here with which this car can take the turn, nearly 28 meter per second. So this is all for this video. In the next video, we will discuss one more numerical problem, and there we will discuss what approach should be taken to solve the numericals. How can we solve the numericals of laws of motion, and what should be our approach to solve them. So see you in the next video.